In the previous lecture, we have seen we have analyzed the negative feedback amplifier in the frequency domain, and we have obtained the magnitude and phase plots of the transfer function. And the purpose of this was to evaluate what happens to the output of the negative feedback amplifier when you drive the amplifier with a sinusoid. Okay. So, this is the magnitude response and this is the phase response. The magnitude is close to the ideal value of k for frequencies well below this pole value omega u divided by k, and well beyond omega u by k it goes off at 20 dB per decade. Now, at the frequency omega u by k, you can see that when omega equals omega u by k, you get k divided by square root of 2. So, k divided by square root of 2 is basically 3 dB below k. So, at omega u by k, it will be k divided by square root of 2 or 3 dB below k. So, the actual magnitude response will do something like this, and this omega u by k is known as the 3 dB bandwidth of the system. So, for a first order system, the bandwidth equals the pole frequency, and the magnitude response of this amplifier at the pole frequency equals k divided by square root of 2, where k is the DC gain or the gain at low frequencies. Okay. Now, when you are drawing Bode plots, we usually do not make such distinctions between 0 dB and 3 dB attenuation, and we show it by straight lines which are asymptotic to it. So, in a Bode plot you do not necessarily have to show this 3 dB, but you have to recognize that at the pole frequency there is a 3 dB reduction in the gain compared to at very low frequencies. Okay. Now, as for phase, at low frequencies the phase lag is small, and then it increases to pi by 4 at omega u by k, and it increases to minus pi by 2. The phase lag increases to pi by 2 at very high frequencies. Okay. So, we will see what happens to the sinusoid when you pass it through this type of an amplifier. So, we know that if the transfer function of the system is h of s and you apply an input, let us say Vp cos omega t to such a system. So, the output will be also a sinusoid, and we know what sinusoid it is going to be. It will be with a magnitude h of j omega times Vp. The amplitude of the sinusoid gets multiplied by the magnitude of the transfer function at the frequency of the sinusoid, and you get an added phase which is the phase of the transfer function at the frequency of the sinusoid. Okay. So, we will examine this for our particular case. So, if we apply an input of Vp cos omega t to our amplifier, the output will be kVp by square root of 1 plus omega square k square by omega u square. Okay. This is Vp multiplied by the magnitude of the transfer function and cosine of omega t minus, because the angle is always negative for this particular transfer function, tan inverse omega k by omega u. Okay. Of course, this is a rather complicated expression, but we have to make sense of it as usual by making suitable approximations. Okay. So, these are the input and output, and first we will look at a frequency range which is much smaller than omega u by k, that is we will be looking at this range of frequencies. Okay. So, in this range of frequencies the output can be approximated by kVp, because this term, the second term under the square root in the denominator, is much smaller than 1, and the angle can be approximated by, we know that for very small values of the argument, tan inverse x approximately equals x. So, instead of tan inverse we simply take the argument of the tan inverse, okay. So, which can be rewritten as kVp cos omega t minus k by omega u, okay. Basically you get an output sinusoid whose amplitude is kVp and you get a delay of k by omega u. Here you see that simply instead of t, the input has omega t, the output has omega times t minus k by omega u. So, this is simply like delaying the sinusoid by a time equal to k by omega u, okay. You also recall that this is the time constant of the system, k by omega u, okay. So, from this we see that for low frequencies, where low frequencies are defined by frequencies much smaller than omega u by k, the magnitude is almost exact, the amplitude of the sinusoid is kVp, that is you still get a gain of k and there is a delay of k by omega u, okay. So, it appears that the amplifier is behaving more or less ideally, right. So, again this is the behavior of the amplifier, approximate behavior of the amplifier for frequencies much smaller than the pole frequency or frequencies much smaller than the 3 dB bandwidth of the system, okay. For these frequencies the output can be approximated by neglecting the omega square k square by omega u square term, as well as approximating the tan inverse by the argument of the tan inverse. When you do that, you see that you simply see a gain of k and you also see a delay of k by omega u, okay. So, the sinusoid is not modified in any way, it is simply delayed. So, if you delay any signal, it will retain its shape. So, what you get for very low frequencies is almost ideal behavior, okay. Now, we can redo the approximation for high frequencies. The output I am rewriting here, okay. Now, for very high frequencies, that is omega much greater than omega u by k, what happens is that 1 is negligible compared to this term and the square root, okay. We get the amplitude of the sinusoid to be kVp by k square omega square by omega u square, which is the same as omega u by omega times Vp, okay. And also you get the argument of the tan inverse to be a very large number, because we are saying that omega is much more than omega u by k. So, this argument is very large, and for a very large argument we can simply approximate the tan inverse by 90 degrees, okay. So, the output for very high frequencies approximately is omega u by omega times V p cos omega t minus pi by 2. Okay. So, you see that first of all the amplitude of the sinusoid has nothing to do with k. Okay. The gain has become pretty much independent of k, it is dependent only on the parameter of the integrator. Okay. And secondly, the sinusoid experiences a phase lag of 90 degrees. Okay. It is not following the sinusoid with a fixed delay, but it has a fixed phase angle of 90 degrees, which means that you can say that it is not following the sinusoid at all. Okay. So, this omega equals omega u by k defines sort of the boundary between the ideal behavior of the amplifier and the non ideal behavior of the amplifier. For frequencies much smaller than this omega u by k, you get almost the ideal gain and the signal is simply delayed, and for frequencies much more than this omega u by k, you get a gain which is unrelated to the gain k. Okay. You get some arbitrary gain that depends on the parameter of the integrator, and also you get a phase lag of 90 degrees. Okay. To summarize, at low frequencies so, this we note is the gain value is ideal and there is a delay of k by omega u. Okay. And also the value of the gain is independent of the parameter of the integrator. See, it depends only on k, which is the gain that you want to have in the amplifier. It is not dependent on what kind of integrator you use, as long as you stay away from, stay sufficiently below omega u divided by k. And for high frequencies, so now gain is not dependent on k. So, the output is given by so the gain is omega by omega u and the output is out of phase with the input. So, we can effectively say that the amplifier is working here because you get the correct gain, you get a delay, but delay is usually of no consequence in most situations. So, you do not worry about it. So, the amplifier is working properly in this situation, and then in this case we can pretty much say that the amplifier is not working properly. Okay. So, the frequency omega u by k divides regions where the amplifier is working properly and the amplifier is not working properly, which is why omega u by k is called the bandwidth of the system. So, it puts a limit on the frequencies that you can apply to the system and still expect proper behavior. In this case, the proper behavior is the behavior of an amplifier. You would like the amplifier to have a gain k, it has a gain k only at frequencies well below omega u divided by k. Okay. So, this amplifier is usable only for sinusoids whose frequencies are below omega u by k, which is why it is called the bandwidth. So, bandwidth simply means the usable range of frequencies. Okay. And for this particular case it is equal to omega u divided by k. Okay. Now, just like in the we analyzed the time domain response and we saw that if you use an integrator with a higher value of omega u, that is if you have a faster integrator, what happens is that it will reach steady state faster. Similarly, here if you have a faster integrator, that is if you have an integrator with a higher value of omega u, what happens is the amplifier will be usable for a wider range of frequencies. Okay. So, the bandwidth of the system is omega u divided by k, and the amplifier will be usable for a wider range of frequencies if you have a higher value of omega u. Conversely, this is usually obtained from the specification. You are usually given the range of frequencies for which it has to operate properly like an amplifier. So, which means that you have to choose an appropriate value of omega u so that it behaves like an amplifier. Okay. So, the result of the frequency domain analysis is that the amplifier is usable for frequencies below omega u by k, which is why this is the bandwidth of the system. Okay. And if you want to make an amplifier with a higher bandwidth, you have to use an integrator with a higher omega u. Okay. So, from this we see that first of all we can make a negative feedback amplifier, but it has some limitations, depends on the kind of integrator that you choose to have. Now, the integrator is described by a single parameter omega u. It describes the speed of the response in the time domain or the bandwidth in the frequency domain, and depending on your requirements you have to choose the appropriate value of omega u. Now, as we go later more and more into the circuits, you will see that achieving higher and higher values of omega u is more and more challenging, and that is where the difficulties in circuit design come in. Okay. Now, let us take a look back at the time domain and frequency domain analysis of our negative feedback amplifier. Okay. In the time domain, we saw that the step response, that is if you have an input step going from 0 to Vx, the output as a function of time will be given by okay, the time constant of this response is k by omega u, and from the frequency domain analysis we see that the pole is at minus omega u by k, which results in a bandwidth to be omega u divided by k. Okay. Now, we have analyzed each of these aspects and we know exactly how it comes about. Certainly, we know that if you increase omega u, the time constant reduces and the bandwidth increases, and this we also know why, because a higher omega u means a faster integrator and the response to a step will be faster if you use a faster integrator. Now, we still have to look at exactly why this quantity k by omega u comes up in many different places. We see that it comes up in the time domain and in the frequency domain. What is the significance of this frequency omega u by k? We already know that it is the pole of the system, but we would like to dig a little deeper into it and see what it means. Okay. So, what is the significance of omega u by k? Why does it appear in all these expressions? Is it just a coincidence or is there something more to it? So, that we can look at by examining the system in the frequency domain and going back to some of the concepts of control systems, negative feedback control systems. Okay. I will redraw my amplifier here. Okay. Now, if you look at the input to the integrator, the input to the integrator is given by Vi minus V naught by k. The input to the integrator is given by Vi minus V naught by k. Okay. So, it has a part that is related to the input to the amplifier, which is applied externally. It also has a part that is related to a quantity inside the amplifier, which is the output of the integrator. Okay. So, the negative feedback part is the second part here, which is basically the output of the integrator being fed back to its input. Okay. So, one of the crucial quantities in the analysis of a negative feedback system is what is known as loop gain. So, it refers to if you inject a certain quantity into the system. So, let me call it V test, what part of it comes back. Okay. So, here we are not interested in the input to the system. So, we will reduce Vi to be 0. Okay. We will reduce Vi to 0 and then I will apply a test input to the input of the integrator. So, what happens is I will get a quantity here which is equal to omega u by s times V test, and here I get omega u by k s times V test. Okay. And at this point I will get the same thing, but with a negative sign. Okay. So, at this point I get minus omega u by k s times V test. Okay. Now, we are talking about negative feedback system, that by definition means that if you apply something into the loop of the negative feedback system, something comes back to it, and here we have evaluated exactly how much comes back. Okay. I have broken the loop at the input to the integrator and then I have applied a voltage V test and it goes around the loop like this, and finally I get back an output which is minus omega u by k s times V test. Okay. I will call this V return, whatever voltage returns to the same point. Okay. or I can define the loop gain. The ratio of V return by V test is minus omega u by Ks, and I will define this to be minus L, where L is the loop gain. Okay. Keep in mind that the quantity that returns at the point at which you have broken the loop is minus Ls, and L is defined to be the loop gain. Essentially this says that if you apply some signal here, how much of it comes back. Okay. So something has to come back, because we are talking about a negative feedback loop. If there is feedback, something has to come back. Exactly how much comes back is quantified by the loop gain. Now let us evaluate the loop gain for this. In our case, the loop gain is omega u divided by Ks. Okay. For our case, the loop gain L of S is omega u by K times S. Okay. Okay. And we can draw the Bode plot for this function as well, and this is very easy because this function also denotes integration, and the magnitude plot of L again on a log scale is a straight line with a minus 20 dB per decade slope. The frequency at which the magnitude of L becomes unity is given by omega u divided by K. Okay. And we can also plot the angle of L. This is not very interesting, it is equal to minus pi by 2 for all frequencies. Okay. So magnitude of L becomes unity at omega equals omega u divided by K. Okay. So again you see this quantity omega u divided by K, but so what? So the unity gain frequency of the loop gain happens to be omega u by K. What physical significance does this have? Actually this has tremendous physical significance. Like I said earlier, we are talking about negative feedback loops. That means that something has to be fed back in the loop. Okay, you apply something here and then something comes back in the loop. Now what comes back is described by the loop gain. So now to have negative feedback loop, it is not enough to have a connection back from the output to the input. A significant amount of feedback signal has to be there. Okay. So what this loop gain signifies is the quantity of the feedback that is there. So you see that below a frequency omega u by K, the value of L is large and there is a significant amount of feedback, and if you go well beyond omega u by K, the magnitude of L is much smaller than 1. Okay. So not much signal is being fed back, although you have a connection from the output to the input, the magnitude of the loop gain is very small, means that there is practically no feedback here. Okay. So in this range of frequencies you have a high feedback or a strong feedback, and in this range of frequencies you have weak or no feedback. Okay. So this omega u by K separates regions where you have a strong feedback and a weak feedback, and that makes all the difference. So you can clearly see that if you have strong feedback, the amplifier behaves ideally, because after all the way we derived the amplifier was by saying that using negative feedback we will adjust the output to be of the ideal value, that is you look at the error between the desired value and the actual value and you drive the output in a direction that will minimize the error. Okay. So that is a negative feedback loop. Now for the error to become very small, the feedback has to be very strong. Now the loop gain is the quantity that quantifies the amount of feedback. Okay. So, if you break the loop in some place, you inject a signal there, and then what comes back to the same point, that is the loop gain. Okay. We exclude the negative sign by convention, but that is the loop gain. Now, you see that for our system, the magnitude of the loop gain is much more than 1 when frequency is much less than omega u by k. That is why for frequencies much smaller than omega u by k, the amplifier behaves almost ideally. Okay. So, we have already seen that from the analysis of the transfer functions. The amplifier is usable for frequencies well below omega u by k. The gain is ideal below this value, almost ideal, and there is simply a delay. Whereas for frequencies much more than omega u by k, there is no feedback. You may have a connection from V naught through the resistive divider back to the input, but there is no signal coming back at those frequencies. So, that means that there is weak or no feedback, and it is not behaving like a negative feedback amplifier at all in this higher range of frequencies. So, the usable range of frequencies is given by this much, okay. And this omega u by k, I will denote it as omega u loop, okay, the unity loop gain frequency, that is omega u by k, and below omega u loop where the feedback is strong, you have almost ideal behavior. Above omega u loop where the feedback is weak, you have non ideal behavior. Okay. You consider our negative feedback amplifier. Okay. And then in this case we are interested in what is happening inside the loop. So, we may as well set the input to 0 and we break the loop somewhere. It actually does not matter where you break it, as long as it is the loop that you are breaking, and you apply something here and see what comes back here, and the ratio of the two we return by V test is given by some minus L of s. We take the minus sign because we already know that we are implementing a negative feedback loop, and this L of s is termed the loop gain. Okay. The range of frequencies where the magnitude of L is much more than 1, there is strong feedback, and the amplifier behaves almost ideally, that is as you expect using the principles of negative feedback. Okay. And the frequencies L of j omega is much less than 1, you have weak feedback and non ideal behavior. Okay. So, what separates these two regions is the unity loop gain frequency. Okay. The unity loop gain frequency is where the magnitude of the loop gain, magnitude of L of j omega becomes equal to 1. Okay. So, this omega u loop or the unity loop gain frequency defines the bandwidth of the system in a negative feedback system. Okay. So, to be able to have a large bandwidth, to have a large range of frequencies where the negative feedback system behaves ideally, you need to have a unity loop gain frequency that is very high. This is again a challenge in the design, as we will see later. What I am trying to do here is to give you an intuitive feel for why we get this omega u by k everywhere. it is not arbitrary and it is not a coincidence. Omega u by k happens to be the unity loop gain frequency for this particular system. So, that sets the bandwidth of the system, and this will be true of every negative feedback system. There may be small changes from that, but the unity loop gain frequency is what sets the bandwidth of the system. So, you expect certain behavior assuming negative feedback, and that behavior will be there only if the negative feedback is strong. Okay, as I have emphasized several times, it is not enough to have a wire connecting from the output to the input, you have to have a significant feedback signal coming back on that wire. So, the regions of frequency where a significant signal is coming back on that wire, that is where negative feedback is strong, and also where negative feedback is weak, is divided by the unity loop gain frequency. The unity loop gain frequency omega u loop, this is the frequency at which magnitude of L of j omega becomes unity, okay, and this divides regions of ideal and non-ideal behavior. And this is simply because it divides regions where there is strong feedback and where there is no feedback or weak feedback, and that is why omega u loop typically is the bandwidth of the negative feedback system. And for the system that we have considered so far, it is equal to omega u by k. We already know that omega u by k is the bandwidth of the system, and k by omega u is the time constant of the time domain step response. Okay. So, we will come back to this later when we do the stability analysis. The frequency at which the loop gain becomes unity is a crucial point for the analysis of negative feedback systems. So, we will come back to it, but here you get a feel for what it means. It divides the regions of strong feedback and weak feedback, and that is why it sets the bandwidth of the system. Okay. So, I have drawn this circuit repeatedly, and this is our negative feedback amplifier, and to make a negative feedback amplifier we have to have first of all a way to take the difference between the input and the feedback quantity. In this particular case it is between Vi and V0 by k, okay, and we have to have a way to integrate the difference. Now, this negative feedback amplifier scheme is so useful that people have put in a lot of effort to put both of these into a single block, and it is a very useful block. So, a block which does sensing or difference between input and feedback, and also integrates the difference, and such a block is known as an operational amplifier or an Opamp for short. Okay. It is an extremely useful block which has probably been used billions of times, and it has a facility to take the difference between the input and the feedback quantity, and it also integrates the difference. Okay. So, the symbol for the op amp is given by where this refers to this particular input and this refers to this particular input. So, by connecting it to these 2 points, you can take the difference between the input and the feedback quantity, and the output is nothing but the output of the integrator. Okay. So, using this op amp we can make the negative feedback amplifier, and it is very easy. I simply reproduce what I have on the upper schematic to the lower one. So, I have a resistive divider k minus 1 r and r. So, this gives me, if this is V naught, this gives me V naught divided by k, and then I apply it to the appropriate input of the op amp, and I apply the input voltage here. Okay. So, this is my basic negative feedback amplifier using op amps, and it is nothing but the realization of the negative feedback amplifier that we have been discussing so far, and this is known as the classical non inverting amplifier. Non inverting simply means that the DC gain is positive, because in this case we know that the DC gain is k, right. The DC gain of this particular system is k. So, you think of the op amp as an integrator, and what happens is the integrator will reach steady state only when the difference between 1 and 2 is 0. So, we will still assume that the input Vi is a constant. The input Vi is a constant, the steady state will be reached only when the difference between 1 and 2 is 0 and the output is also a constant. Okay. So, when that happens, the output will be exactly k times the input voltage, and we get our ideal amplifier. Okay. So, the op amp is nothing but a block that can take the difference between 2 signals and integrates it to drive the output. Okay. And the op amp is described by a single parameter, which is the parameter of the integrator. Okay. So, the op amp has a certain omega u. Omega u is the unity gain frequency of the op amp, and this is the most important parameter in the op amp. Okay. If you look at any op amp data sheet, you will see the unity gain frequency listed. Typically it is listed in hertz. We have been using omega u, which means that our omega u is in radians per second, but whatever it is, once the unity gain frequency of the op amp is known, you can calculate either the time constant or the bandwidth of any circuit that you make using the op amp. Okay. So, we also know that V naught by Vi will be k by 1 plus s times k by omega u for this particular amplifier structure. Okay. Now, there is also a concept of an ideal op amp. If you go on increasing the unity gain frequency of the op amp, if you go on increasing the value of omega u, what happens is the bandwidth of the system goes on increasing. Okay. Bandwidth of the system is given by omega u divided by k, and if you go on increasing the value of omega u, the bandwidth goes on increasing. Okay. Now, if you set omega u to be infinity, then the bandwidth will be infinity. So, that means that for all frequencies the gain of the system will be k. The transfer function will not have any s terms in it, the transfer function will simply be equal to k. Okay. When the op amp is an integrator with a unity gain frequency omega u, it behaves ideally for DC, that means the DC gain is k. Okay. So, we know that if you apply a constant Vi, finally a steady state is reached where the plus and minus terminals of the op amp are at the same voltage and the output equals k times Vi. So, it always shows ideal behavior for DC inputs. Okay. Now, if you set omega u to be equal to infinity, the bandwidth becomes infinity and it shows ideal behavior for all frequencies. Okay. So, this is what is called an ideal op amp. Ideal op amp simply means it is an integrator with omega u tending to infinity. So, what happens in this case? For any frequency, V naught will be k times Vi. Okay. The negative terminal of the op amp will also be equal to V naught by k equals Vi. Okay. And the difference between these two terminals, that will be equal to 0. Okay. So, that is the definition of an ideal op amp. So, many times the ideal op amp is presented first and then you are shown the actual op amp. We have gone the other way, we have gone from first principles to try and derive a negative feedback amplifier. For that we see that we need a block that senses the difference between two quantities and something that integrates the difference, and we can arrange it as a negative feedback amplifier. So, that is an amplifier in which the error is gradually driven towards 0. Okay. So, such a block, when you have an integrator, behaves ideally when the input is constant. When the input is constant and you wait for the output to reach steady state, the error or the difference that is sensed will eventually become 0. Okay. In steady state the error will be 0. Now, if you make the speed of the integrator unlimited, then it does not matter how the input is changing, always the output will be able to track the input. Okay. So, such a concept is known as an ideal op amp, and it is a very useful block for analysis and sometimes for coming up with circuits and so on. And of course, later you have to recognize that every real op amp has a finite value of omega u and then put that and analyze it. But nonetheless, the ideal op amp with omega u equal to infinity is a useful concept to analyze, and basically the behavior of that op amp is given by the fact that the difference voltage between the plus and minus terminals of the op amp equals 0. Okay. So, using that you will be able to analyze any ideal op amp circuit, and this is a good first step. So, let us say you see an op amp circuit that you have never seen before and you think that it is an op amp a circuit that uses negative feedback, then you can assume that the op amps are ideal, meaning the input terminals of the op amp are at the same voltage, that is the error in the negative feedback system is 0, and go ahead and analyze it. After that you can put in all the details to the circuit and then analyze the circuit.